Hello, everybody, and welcome back to today's math video. Today, we are going to be learning and talking about solving logarithmic equations. I'm kind of sort of making you guys a little mini series about this, chunking the information, chunking different strategies so that it's a little bit more manageable, a little bit more digestible, and easier to handle. So get out your calculators, get out your piece of paper, get your writing utensils. Let's get prepped and ready. And without further ado, let's hop right into this thing for part one of, I don't even know how many. Not a whole lot, but like at least a couple. um, so last week when we started talking about solving logarithmic equations, the first two situations that you're going to come across, we had discussed in class, but we're going to kind of expand and talk about them a little bit further in depth today. So the first type of logarithmic equation that we're going to talk about and study today is when we have log or the natural log on one side of our equation. And one strategy for solving log equations is to isolate the logarithm and then convert into exponential form. And we saw this last week as we had like very simple problems where it was just a log on one side and it was equal to a number or a variable or something. We converted to exponential and we're able to solve quite easily. To start off, we're going to do also a pretty fairly simple equation as well, except the log or the natural log will not be isolated yet. So let's see what we can do. Let's hop into it. Let's get into our first example. Our first example is log of 6x minus 3 equals -4. Okay, so you can see here that there is log on the left-hand side. However, it's not alone. We've got this -3 guy chilling over here. So I have log base 10 of 6x minus 3 is equal to 4 is our equation. And remember, the strategy is to isolate the logarithm. And when I say isolate the logarithm, I mean just use any inverse operations to get it alone. Get the logarithm alone. And then once we do that, we'll be able to convert to exponential and proceed with like business as usual. So I've got log base 10 of 6x minus 3 is equal to -4. My inverse operation of subtracting 3 is going to be adding 3 to both sides. When I do so, my resulting equation is log of 6x. -4 plus +3 is -1. Cool. Now my logarithm is isolated. Check. Now I just need to convert my equation into exponential form. Remember, a log without a base given is log base 10. And you can exponentiate both sides, giving it 10 raised to the log base 10 of 6x, and they would cancel out. Whatever you do to one side of the equation, you must do to the other. Or, y'all know me, I like to roll my log into exponential form. So I say 10 to the -1 is equal to 6x, everything inside the parentheses. And from here, we just use any skills that we already have or already know. So for example, if this was like 10 squared, I would use my calculator and say 10 times 10 is 100. However, I have 10 to the negative exponent. Negative exponents mean we're going to need to use the negative reciprocal. We're going to need the inverse. So 10 to the -1 is actually 1 over 10 to the first power is equal to 6x. I made a simple substitution. And then I know what 10 to the first power is just 10. So I really got just 1 over 10 equals 6x. Now my goal of solving anything is to figure out what the variable is equal to. In this instance, our variable is the letter x. So I need to get x alone. To do so, I am going to need to divide by 6 on both sides, but I'll have a double-decker equation. That's okay. If I divide by 6 on both sides, that really means I'm multiplying by the reciprocal. So I have 1 over 10 times 6 is equal to x, or 1 over 60 is equal to x. However, if that doesn't sit well with you, if that's kind of weird for your brain to handle, what I like to do, and you'll see that we arrive at the same solution, is get rid of this denominator first. Get rid of that 1 over 10. So multiply both sides by 10, multiply both sides by 10. So now I have 1 equals 60x. And I can see here, if I divide both sides by 60, I end up with 1 over 60 is equal to x. So either of those strategies will work. And yeah, we were able to work with this log equation that wasn't quite isolated, but then it was. So what happens if we have a log equation that is isolated, but it's a little bit more complex? Let's try one of those. Next example is going to be log base 3 this time of x squared minus 7x plus 15 is equal to 1. Again, notice that we do have a log expression on one side, and in this instance, it does happen to be isolated, meaning that there's not like anything being multiplied, divided, added, or subtracted to this log expression. So conveniently, we're able to go ahead and just convert the equation into exponential form because it is already isolated. So 3 to the first power is going to equal everything inside our parentheses here. It's equal to x squared minus 7x plus 15. And once you convert to exponential form, remember, it's game on for anything that we're able to do. So 3 to the first power, we know that's just 3. Hint, whenever you have an x squared term, whenever you have a quadratic term, that's probably meaning we're going to have to factor. So in this instance, to factor this expression, I need to get everything moved over to one side. So I'm going to subtract 3 from both sides. I end up with 0 is equal to x squared minus 7x plus 12. 15 minus 3 is 12. Now I'm going to need to find factors of 12 that add up to 7. I have, remember, 1 and 12, 2 and 6, 3 and 4, and this one's going to do it for me. 3 times 4 is 12, but negative 3 minus 4 more is negative 7. So I'm going to say negative 3 times negative 4, and negative times a negative is positive, and a negative 3 plus negative 4 gives me negative 7. So I end up with 0 is equal to x minus 3 and x minus 4. Now, since I have 0 equal to a product, the only way this will be true is if each one of the parts of the product is equal to 0. So by the 0 product property, I end up getting x equals positive 3 by setting x minus 3 equal to 0. And x is equal to 4 by setting x minus 4 equal to 0 and solving. So I have 2 possibilities. Cool. Now, something we'll have to keep in mind with logarithmic equations is that unfortunately we could potentially get extraneous solutions, okay? So luckily for us, extraneous solutions arise most often when we apply properties of logarithms or we have a quadratic equation to solve, because then we're getting negative values potentially. So something I want to just bring to light and start to nip in the bud right away is that just like most other functions that we've been studying so far, we are going to have to check that we don't have any extraneous solutions. Remember, extraneous are extra, they're liars, just like your ex. We can't trust them. They're not the one for us, okay? Something I want to bring up, though, about extraneous solutions is that logs are only defined for positive numbers, positive inputs. So Negative numbers or negative inputs are undefined with logarithms, and this will be discussed a little bit further, more in depth when we talk about the graphs of logs, and it will make sense looking at our graph why we only have positive numbers, positive values that are defined for logarithms. But so here, since we have 3 and 4, those are both positive values. They should work out, but I'm going to show you how we can check for extraneous solutions. So to check for extraneous, you just check it back in the original equation. So I'm going to plug in log base 3, 3 squared minus 7x plus 15 should be equal to 1, right? So if I plug it in, I would have log base 3 of 3 squared, which is 9, minus 7 times 3, which I believe is 21. Yep. Plus 15, which is equal to 1. So then I have log base 3 of 3 is equal to 1, and that's a true statement. I don't know if you guys remember if we had log base b of b is equal to 1, but we can verify this by converting to exponential. Is 3 to the first actually equal to 3? Yes, it is. So I do know that when I plugged in x equals 3, that's a true equation. Then I would repeat the process for x is equal to 4. So I'm just going to substitute those values back in here and check again. So I still have log base 3 of 4 squared, right? 4 going here, 4 squared, which is 16, minus 7 times 4, which is 28, 7 times 4, plus 15. And 16 minus 28 plus 15, working inside of those parentheses first, gives us 3. Again, we have log base 3 of 3 is equal to 1. That's what we just had. But again, if you don't quite remember this, when the base and the input value are the same, it should equal 1. But you can roll your log or convert to exponential to verify 3 to the first is actually equal to 3. Is true? Yes, so both of these solutions, both positive values, are true solutions for this logarithm. Okay, so the next problem that we're going to talk about here is going to deal with the natural log, because remember, natural logs follow the same properties of logarithms. Natural logs are just a log with the base of the number e, which is Euler's number. So the next problem that we're going to encounter is the natural log, lowercase l, lowercase n, of x minus 3 quantity squared is equal to 4. So there's a couple different ways to do this problem. I'm going to show you 2 of them. So the natural log of x minus 3 squared is equal to 4 is what we're going to tackle. And it's important that we remember that the natural log of x is log with the base of the letter e of x. Now, e is Euler's number, and it is 2.718281828. It comes up frequently in science and in nature all the time, warranting its own variable, its own letter, kind of like pi. So in order to do this problem, you might want to fill in, like log without a base is 10. Natural log has a base of e. Now, notice that this natural log is isolated on one side. It is completely alone. There's nothing else I can do here. So it is isolated and convert the equation to exponential form. So since that's what we've been talking about, I'm just going to go ahead and do that. So e raised to the 4th power is equal to everything in the parentheses. So we have e to the 4th power is equal to x minus 3 and squared. Now, this is where you're going to need your calculators. Remember how I said to get them ready? There is a button on your calculator that says e to the x. Now, on mine, it's right here, right above the ln. It's kind of hard to tell. I'm sorry about that. But it says e to the x. I hit my second button, and it will show me e raised to a specific power. So I can just plug in the number 4, and it will give me a decimal approximation, 54.59815003. Okay, if you don't have a fancy schmancy calculator like this, you definitely can use your regular, like, iPhone calculator. Remember, if you turn it sideways, it becomes a scientific calculator. And what do you know? The second button to the left of 7 is e to the x. So you hit that, e to the x, and it's assuming 0. So with the iPhone, you have to type in the power first. So 4 e to the x, and you'll notice I have the same result, 54.598.15003. This one actually has way more digits to it, but that will work. So I could plug in that number, and since it's, an approximation, we could say e to the 4th is about 54 point, I'm just going to say 598. It's about 54.598 if I round to 3 decimals, is equal to x minus 3 squared. And of course, we want to solve for our variable. So we can take the square root of both sides to eliminate this square. That will leave me with x minus 3 and the square root of 54.598. So if I take the square root of e to the 4th, I get 7.389 approximately. And to continue solving this for x, I'd add 3 to both sides. So 7 plus 3 is 10.389 is equal to x, is what I get. Now, notice that I used my calculator to figure out what e to the 4th was. I could have just left it and took the square root of both sides just like I did in the second step. I could have said, okay, e to the 4th, right? We have this right here. E to the 4th equals x minus 3 squared. And I could have just done this. Boom, boom. I still, on the right-hand side, the square root of a square will just leave whatever was being squared. So in this case, x minus 3. And remember, the square root has an index of 2, or a rational exponent of 1/2. So you have 4 divided by 2, which gives us just 2. So I have e squared equals x minus 3. And I could have just added 3 and said my answer was e squared plus 3 is equal to x. And from here, I could have used my calculator. So I would have found e to the second power, and then just added on 3. Notice how in my calculator I can type e squared plus 3 and hit it, and I get 10.39 or 389.0561, whatever floats your boat. So you get 10.389. And I'm going to use these like squiggly values for approximately equal to, since I am taking a decimal approximation of it and I'm rounding. Now, there's one other way that I could have approached this problem. I could have used the power property and divided both sides by 2. So I'm going to show you that really quick. As an alternative, the natural log of x minus 3 squared is equal to 4. And if I wanted to make sure the first part was really, really isolated, I mean, I guess it's kind of overkill, but I guess I could have used the power property of logs, because all of the properties of logarithms apply to natural log as well. So it would have 2 times the natural log of x minus 3 equals 4. And to isolate my natural log, I could divide both sides by 2. Whatever I do to one side, I have to do the other, leaving me with the natural log of x minus 3 is equal to 4. Or I'm sorry, 4 divided by 2 is 2. Again, Natural log base is e, so I would have e squared is equal to x minus 3. Notice I'm back here to e squared equals x minus 3. And add 3 to both sides to get back to where I started. E squared plus 3 is equal to x, or we found out with a calculator that 10.389 is about the value of x. So that's pretty cool. 3 different ways that end up with the same result. Remember, if you can do a problem in multiple ways and end up with the same result, it is like 99.9% chance that you did it correctly. And let's do one final natural log problem where we have the natural log just on one side. And no, there's not going to be a bunch of fancy different ways to do this one, so don't worry. Okay, so the last problem where we're going to have a log or a natural log on one side is this example. We're going to take the natural log of a 4a squared and have it set equal to 3. The natural log of 4a squared and set it equal to 3. Now, luckily, this one isn't too bad because the natural log, is isolated. It's all alone. This is the quantity that it's being evaluated at. So sometimes I like to just put parentheses around it so I know that my natural log is isolated. Then I can convert the equation into exponential form. We know that the natural log has base of e. So I will convert. I could either exponentiate both sides by raising the base of each exponential equation as e to the natural log will cancel each other out because they are inverses. Or I like to just convert to exponential form. The base of the logarithm is e, so the base of my exponential is e to the third power is equal to 4a squared. And this is where my calculator is going to come in handy again, right? I need to solve for a, so it only makes sense that I divide both sides by 4. I end up with a squared is equal to e to the third divided by 4. And to solve this and get a alone, I would take the square root of both sides. The square root of a squared is a, and then I have the square root of e to the third divided by 4. Now this is where I want to grab my calculator and figure out what e to the third divided by 4 is, and then take the square root of it. So grabbing my calculator, I'm going to take e, put it to the third power. So I get 20.08553692. I'm going to divide that number by 4. That's e to the third divided by 4 is 5.021384231. And then I'm going to take the square root of that number. And I'm going to raise it to the 1/2 power because I find that that's easier in my calculator instead of hitting the square root button and typing in that entire value. Because remember, square root is 1/2. So when I do that, I get 2.240844, blah, blah, blah. So A is approximately, I'm just going to go to 2 decimal places, 2.24. But remember, with square roots, you have the positive value and the negative value. And whenever we have a quadratic, we want to check that we don't have any extraneous solutions. So I'm going to check that over on the right. Remember, extraneous solutions arise most often when we apply properties of logarithms or have a quadratic equation to solve. Since I had an a squared term, I technically had a quadratic equation to solve, and logs are only defined for positive numbers. So let's check, because I've got a negative here. Let's check and see if this is extraneous or not. Now remember, when we check extraneous, we check in the original. And since I took a decimal approximation, as long as it gets really close to 3, that will be fine. So I want to see if the natural log of 4 times negative 2.24 squared is equal to 3. So luckily, a negative number squared will always be positive. So negative 2.24 squared is 5.0176. And 4 times 5.01 is 20.0704. And I want to know if the natural log of 20.0704 is about 3. So I just find in my calculator the natural log button. It should be really close to log. And type in 20.0704. Again, this is an approximation, so it should be really close. Well, it's 2.999. I'd say that that's close enough. So my negative value that I was worried about actually works in this instance. And my positive value will work as well. It will work out to be exactly the same because a positive number squared is still positive. Awesome.